Let's go to solve a 2D wave equation. Remember that the wave equation also has a dependency on time. So this is a three-dimensional problem, two spatial dimensions and one time dimension. So let's look at it. We have a rectangle, 0 to a times 0 to b. And in this rectangle, we want to satisfy the wave equation. So c squared times nabla squared w equals second derivative of time of w. We can write it in multiple ways. We can write it with nabla squared, we can write it with delta, or we can write it as the sum of the second derivative with respect to x plus the second derivative with respect to y applied to w. Either way, they're all equivalent ways of writing the wave equation. We set a boundary condition that is just a trivial Dirichlet boundary condition on all of the boundary. So we just set w equal to 0 everywhere on the boundary of our rectangle. And we set an initial condition. We want w at time 0 to take a certain value f, that is a function of x and y. And we set 0 initial velocity. So it's really the idea that we have displaced our membrane in a certain position, and at time 0 it's fixed in that position, and we just let it go and see how it oscillates away. We're going to use separation of variables. And this is an interesting example because now separation of variables requires three variables. It requires separation with respect to x, y, and t. The idea by which it's easy kind of to make separation of variables in the wave equation in 2D is that all our derivatives are independent of each other and our axes are perpendicular. So we are trying to figure out how to completely detach the y direction from the x direction from the t direction that we don't see in this projection, but it's somehow perpendicular. If this works, then we have a good separation of variables solution. So if we apply the various derivatives, what we find is that x second yt plus x y second t is equal to 1 over c squared x y t second. And we try to separate things away. We divide everything by x, y, and t. And we retrieve a block that is x second divided by x plus y second divided by y equal to t second divided by c squared t. Remember that the primes are derivatives with respect to different variables. So in this situation, we have the first block that depends only on x and t, and the second block, the first block depends on x and y, and the second block that depends only on time. So since they depend on different variables, they have to be constant. So we set this equal to minus k squared. And now we look at the first block. X second divided by x plus y second divided by y. We forget the part depending on t, equal to minus k squared. And we split again x from y. So now we have x second divided by x equal to minus k squared minus y second divided by y. And the first block, x second divided by x, is only a function of x. And the second block, minus k squared minus y second divided by y, is only a function of y because k is a constant. So this has to be, again, equal to a constant. We're going to set both these functions equal to minus m squared. We have trivial boundary conditions in both directions. So the idea is that if we're careful enough, we should get a Sturm-Liouville problem both in the y direction and in the x direction. And since we have two variables that we have just introduced, k squared and m squared, we have enough freedom to find all the necessary eigenvalues. So now we have x second divided by x is equal to minus m squared, and y second divided by y, shuffling things around, is equal to minus k squared plus m squared. And we're going to set this equal to minus n squared. And this works because we can rewrite k squared is equal to m squared plus n squared. M squared comes from the Sturm-Liouville problem in x, so it's expected to be positive. N squared comes from the Sturm-Liouville problem in y, so it's expected to be positive. So a sum of positive squares is again a positive value. So now we have split it successfully into two Sturm-Liouville problems. We have on one hand the Sturm-Liouville problem in x, and on the other hand the Sturm-Liouville problem in y. And they are independent. There is no overlap between the two. On one hand, we have x second plus m squared x equal to 0, with trivial boundary conditions. X0 equals x at a is equal to 0. And on the other, we have a very similar format. Y second plus n squared y equal to 0. Y0 is equal to yb. Y computed at b is equal to 0. They are independent. And that's why we need to be careful. We have to remember that the solution with respect to y, the solution of y and the solution of x don't depend on each other at all. That means that when we solve for the eigenpairs of x, we want to count them on an index that I have introduced that I call j. Well, when we introduce the eigenpairs of y, we want to count it on a different index, so L. L and j are completely separate. They come from different places. They come from the idea that x, the y direction and the x direction are perpendicular and don't interact. So now I have an eigenpairs for x, that is mj, where mj is equal to j pi divided by a, and j spans the natural numbers, so 1, 2, and so forth. And phi j equals sine mjx. While the eigenpairs for y are fairly similar, but they're different things. So even though they look the same, they're different things. We have NL, that is defined as L pi divided by b, and psi L is equal to sine NLy. I don't care how you call these variables. The Greek alphabet is not a requirement for this course. As long as you call them two different things and they keep being different, go for it. Anyway, now we have the eigenpairs for y and the eigenpairs for x. Combining them give us values for k, because the eigenpairs for x give us value for m, the eigenpairs for y gives that value for n, and we can combine them in any way to create a k squared that fits in our initial equation. So we have mj and nl. If we want to compute k squared, we have to think that k squared is a sum of any mj and any nl. So when we're looking at k has two indices, has both the j index from m and the l index from n. So now, when we want to solve the equation for time, we have to keep track of these two indices. So we have the second derivative of time plus k squared c squared t equal to 0. And I have placed indices j and l everywhere to remind you of all the things that depend on which choice of mj and nl you have done. So we can write the solution for the time being t as index j and l being a sum of a sine c kjlt plus b cosine of c times kjl. And now combining all the results from the Sturm-Liouville problem in x, the Sturm-Liouville problem in y, and the OD in t, we have the W, our solution of the wave equation on the rectangle, is an infinite sum on j and on l. So both j and l go from 1 to infinity, and we have tjl, x that only depend on j, and y that only depends on L. And if we replace this by this blob in which we notice the sign that depends on NLY, the sign that depends on MJX. This is where the J and the L pop up, and we have explicit formulas for MJ written at the top and NL written at the top as well. And this blob, box depending on Y and box depending on X, determine the box depending on T. That is AJL sine CKJLT plus BJL times the cosine of the same thing. So once you fix J and you fix L, you have fixed all the terms in this box. And now I have to introduce the initial conditions. How do we do that? Let's start by introducing the first initial condition. We want W at time equal to 0 being equal to F. And we write W at X and Y time equal to 0 as an infinite sum on J and an infinite sum on L of BJL sine of a box depending on X, sine of a box depending on Y. We can think of this as the fact that we have a function. I want to think of it as if we were considering X a constant. So we're varying Y, and we have F that depends on Y, and sine that depends on Y. And the coefficient in front of sine that depends on Y is an infinite sum over J from 1 to infinity of something that depends on X. But now that we're thinking of X being fixed, we remember that sine NLY is the eigenfunction of a Sturm-Liouville problem. Again, so we can find the value of the infinite sum of BJL sine MJX as a coefficient, all of it as a coefficient in an infinite sum of eigenfunctions of a Sturm-Liouville problem. And we want that to be equal to f of xy. So we can use the standard formulas. And here we're only thinking of y as a variable, x is a fixed constant. So then we have this infinite sum on BJL sine MJX being equal to a fraction between the inner product with respect to y of f of xy sine and ly divided by sine and ly inner product with itself. And this inner product is the integral from 0 to b with respect to dy. And now that we have written everything out, well, we notice that our left-hand side and our right-hand side are both functions of x. Not only that, but our left-hand side is an infinite sum of a coefficient times sine mjx, that is the eigenfunction of a Sturm-Liouville problem itself. So now we can do the same trick in the x direction. So we can write it all down as BJL being the inner product with respect to x and the inner product with respect to y of f times sine mjx, that is the box with respect to x, sine nly, divided the inner product with respect to x and y of the two sines times each other. And if you want to write it all out, is really this integral from 0 to a and from 0 to b with respect to x and y of f of xy, the sine with respect to x, the sine with respect to y, divided the same integral from 0 to a and 0 to b of sine mjx times sine nly, all of this squared with respect to x and y. Might be complicated to compute, but it's just the application of the Sturm-Liouville problem over and over again.